Let's do a little proof problem using FTA, Fundamental Theorem of Arithmetic. It's not going to use it in some super complicated way, but it really has that as the background. So let's let P be a prime number and let N and D be natural numbers. So here's the deal. D is a factor of P to the N. So we're really looking at a prime power, and we're looking at something that's a factor of a prime power. And I want to show that that has to be very, very simple. Hopefully, if you're in the mindset of fundamental theorem of arithmetic, this should seem pretty obvious. We'll do a numerical example in just a second. But we want to prove that D actually has to be just a smaller power of the same prime. So P to the M for some natural number M with 0 less than or equal to N. 0 less than or equal to M less than or equal to N. So for example, the only factors of 125 are 1, 5, 25, 125. Okay, how would we prove this really carefully? And I want to prove it using FTA in a small way, but not like, you can prove it in a kind of a messy way with lots of subscripts and superscripts and things like that. Okay, so we know that I want to show that if Q is a different prime, Q not equal to P, then Q does not divide N, or does not divide D, rather. Okay. Well, let's see. Let's just do a very quick proof by contradiction. If Q divides D, and D divides P to the N, okay, then Q is a factor of P to the N. Oops. But wait a minute. P to the N, that is the prime factorization of P to the N. You're looking at it. It doesn't have a Q in it. So that's impossible. Okay. So in other words, there's no prime other than P that can divide Q. So only P can divide Q, and hence, again by FTA, fundamental theorem of arithmetic, when I prime factorize D, I can only get P to some power. So we know it's P to the M. Okay. Now we just need to show that that M can't be bigger than N. Well, that's pretty easy. Okay. If M were greater than N, then of course D would be greater than P to the N, because D is equal to that power of P, which again contradicts the fact that D was supposed to be divisor of P to the N in the first place. Okay, so just to have a little bit of use of FTA to realize that anytime I think of an integer, I can just immediately go to its prime factorization. And this said its prime factorization can't have anything else, and then this easily says its prime factorization can't have more p's than the thing I'm dividing. Okay, so in fact, 0 is less than or equal to m is less than or equal to n. And we're done. And that's it. So there's problems certainly that get more complicated, but that's kind of a basic problem using FTA.